Good day, everyone, and welcome to our channel where we're trying to fix any problems students have at the primary math level. Today, we'll be looking at the secondary entrance assessment and specifically the past paper questions from 2019 in the first section, all 20 questions. Don't forget to like the video and add any comments down below so we can help create other videos to assist you in any areas that you are having problems with. We also have channels for students who are struggling at the Form 5 CSEC math level and at the additional mathematics levels as well. All these are linked in the description down below, where we also show what order you should go through all the SEA videos in order to get a better grasp of the entire syllabus. Let's now look at how the questions are distributed across the first 20 questions of this paper, which is section 1. Let's remember that the strands are 4 in primary school, the first being number. Remember, strands means the 4 major topics. So the first topic of number took up half of the syllabus. So that means in the first 20 questions on this paper, questions from number 1 until 10 are based on number. The next strand is measurement, which includes weight and time and distance, area and volume, and that is tested in numbers 11 to 14. The following strand is geometry, looking at 2D and 3D shapes, and that is tested for 3 questions, 15, 16, and 17. And the last strand, statistics, will make up the last 3 questions in section 1, 18, 19, and 20. Let's now look at number 1, where it states write the value, not the place value, but write the value of the underlying digit in the place value chart. So we can easily recognize that this is a 1, 2, 3, 4, 5, 6, a 6-digit number. And they're looking for the value of the 5th digit. So some students can easily identify it and recognize that this is the answer, 30,000. But for those students who are getting problems, let's recall one way in which your teachers may have shown you it, which is if we think about the same place value and we start from the right hand side, which is the smallest whole number, the value will be ones, and then what follows will be something 10 times bigger because this is a decimal system. So that will be tens. And what is 10 times bigger? That will be 100. So we have ones and tens and hundreds. And that itself forms one group. Remember, math is a pattern. So just as we saw ones and tens and hundreds, then what comes next? That will be ones as well. And what follows after? Tens. And what comes next? As we see the pattern, ones, tens, hundreds from the right hand side. Then we're seeing ones, tens, and what will come next? Hundreds as well. As such, in this idea of place value, it's the same 3 places that are being repeated over and over. So ones, tens, hundreds fall within the family of ones, and the next set, ones, tens, hundreds, fall within the family of thousands. So if we look at the actual question, they're asking us to find the value of the underlying digit, that number 3. So if we identify this here and we're looking at the place value, we can see that it's telling us the place value there is 10. And what 10? It will be 10,000 because it falls within that period. And now that we know the place value, let's include the idea of the number 3. So it will be 3 sets of tens thousands. So the value of the 3 will be 3 times 10, which is 30,000. Let's look at number 2. What is the largest prime number in the box below? And some of us can easily recall this because our teachers encourage us to memorize all the prime numbers. And they can say, well, the answer is 67. Because 75 is not a prime number, 87 is not a prime number. But let's do a little revision of how prime numbers are understood. So if we look at the number 1 and we think about bringing up a square, one square to represent that, then our square will be with a length of 1 and a width of 1. As such, we have 1 times 1 if we want to find it. So that is a square number. Now, if we consider the idea of the number 2, and we have two squares and we want to form a shape with it, we can easily form, if we put them next to each other, 1 and 1, that will give us 2. So we can form a rectangle. And that rectangle has one side being 1 and the other being 2. So we can form a 1 by 2 rectangle. And we can actually turn it the other way and will give us it vertically, one on top the other, which is still a 1 by 2 rectangle. Now this shows that 2 is not a square number. And if the number only is able to form one type of rectangle, we have a special name for that. And that is called a prime number. Let's go on to number 3. And if we're forming the rectangles again with 3 squares, we're going to get 1, 2, 3. So we're going to get a 1 by 3 rectangle. And if we turn it the other way, it's still going to give us the same type of rectangle. But can we form any other shape with these 3 squares? No, we can't form a triangle. We can't form a square. So since we're only getting this basic rectangle, 1 high by however long, 2 long or 3 long as the case may be, then that is also a prime number. Now let's try the number 4 as we're doing a little revision before we solve the question. Let's look at the number 4. If we have 4 squares and we put them next to each other, we will get 1, 2, 3, 4, forming a straight line, which gives us a 1 by 4 rectangle, length by breadth, in order to find the area. That's what we're doing. Can we rearrange this to get another quadrilateral? Well, we can. We can connect it 1, 2 on top of it, next it, 3, and on top 4. So now, what does this tell us? It tells us that 4 is a square number and a prime number. Since it's more than one thing, then the word to show that there's more than one shape that's being formed is the word composite. So 4 is called a composite number. So if we look at this, and we're specifically in this question looking at a prime number, prime numbers will be ones in which we only find a long rectangle, 1 by something. So let's start with the largest number and see whether or not that is a prime number. So we know that all of these numbers will give us a thin long rectangle, 1 times anything. So 1 times 41 will give us, for the first one, 1 times 75, 1 times 49. For each, all 6 of them, you will get a rectangle looking like that. 1 and itself. Now, if we think about this chart here, where we can list all the numbers and see what is the other number that goes with it, we know for 87, right, we will get a 1 by 87 rectangle. Can we form any other rectangle? Right? So we understood 1, so we could take that off and look for any other shape. If we're only getting this 1 by itself rectangle, then it looks like the number 2 or the number 3, so it's a prime number. If we can form more than that and another type of rectangle, then it will be a composite number. So let's see for 87. What else can go into that? Well, we know 3 into 87 is 29. And if we're getting problems to remember that, we know 2 can't go into it because 2 does not go into a number ending with 7. So we try 3. And if we're trying 3, some of us will know that if we add 3 to 87, we will get 88, 89, 90. How many 3s are there in 90? 33s. So if 30 3s is 90, and we take out one group of 3, we have 29 3s. So 3 times 29 is 87. So when we're looking at the number 87, it forms a long rectangle, so it might be a prime number, but it also forms another type of rectangle. And since it's forming more than one type of rectangle, then it is not a prime number, but a composite number. Let's now look at what is the next largest number. And in these 6 numbers that were given in the box, after 87 is 75. So we're sure that 1 times 75 will give us that thin long rectangle. So it is a prime number to start with. It has those properties. And let's see what else can it get. Can 2 go into 75? Well, 75 ends with a 5. 2 goes into any number that ends with 2. 1, 2 is 2. 4, 6, 8, 10, or 0. So therefore 2 cannot go into 75 evenly. As such, we have to try 3. And we all know if we count our money, if we have 3 25 cents, 25 cents, 50 cents, 75 cents. So 3 25s are 75. So that means that we're forming a different rectangle, not just the 1 times 75, but the 3 times 25. So since we're finding 2 different rectangles at least, it means that 75 is a composite number. And we try those. So what comes next? Since 87 didn't work, 75 didn't work, let's go look at the next biggest number, which is 67. So we know 67, just like all the other numbers, will give us the first thin long rectangle, 1 times 67. And can it now, let's check the others. Can 2 now go into it? It cannot, because 2 cannot go into a number ending with 7, just as it could not go into 87. And if 2 cannot go into 67, it means that 4 will never be able to go into 67, 6 will not be able to go into 67, 8 will not be able to go, because if 2 can't go into it, 8 can't go into it. Look at our 2 times table and look at our 4 times table, or 6 times or 8 times. All of them are even. And 10 will not be able to go, and 2 could go into 12, and if 2 can't go into 67, 12 won't be able to go into 67. So we knocked out all the even numbers. So the next number we try is 3. Can 3 go into 67? Well, 3 can go into 60. That gives us 20. 3 $20 bills is $60. And what do we have remaining? $7. So can 3 go into 7? 1 3 is 3. And next group of 3, 3 and 3 is 6. And next group of 3 will give us 9. So 3 will not be able to go into 7 without a remainder. And if we try 5, any number that 5 can go into without a remainder will either end with 5. 1 5 is 5, 2 5s are 10, 3 5s are 15, 4 5s are 20. So any number that 5 can go to will either end with 5 or 0. So 3 does not work, 5 does not work. What about 7? 7 tens are 70. So 7 cannot go into 67 without a remainder. What about 9? 9 into 60, what number? 6 and what number gives us 9? 6, 7, 8, 9. So that's 3. So 6, 3. 63 is the number 9 can go into without a remainder. Cannot go into 67 then. 11 6s are 66. 13 5s are 65. So no other number forms a rectangle, and since none of these numbers can go into 67 except for 1 and 67 itself, then 67 is a prime number. Number 3, write 39 over 5 as a mixed number. So there are multiple ways to do this. And we know some students will easily be able to say 7 and 4/5. And let's see how we got that. We can first of all represent a whole in different shapes. In this example, we'll be using it as a circle. And how many parts should we break this up into? We should break it up into 5 parts. And what tells us that? The denominator. It says that we're considering each whole with 5 parts in it. So, recognizing that, we can shade all 5, and that tells us that there are 5 parts in it, and we can represent it differently as well in terms of the idea of a number line, or a number chart, or even a 100 board. So I will pull out the example of the 100 board here in rows of 5, as teachers use different ways of representing the same. And again, if that's the first whole gives us 5 parts, how many parts do we want in all? The numerator tells us that 39. So we haven't reached there as yet. So we could bring up another whole, which means another 5. So that gives us 5 and 5, 10 parts. So 2 wholes will be 10 parts out of 5. And then we add another whole. So that would mean another 5 parts. So it indicates that we have 15 parts or 15/5. That's the same as 3 wholes. Continuing, we're going to go to 4 wholes, and that's going to give us 4 5s are 20. So we have 20 over 5. And then as we continue, as we head towards it, we're going to get a 5th whole, and that's going to give us 5 5s are 25. Continuing, another 5. Did we reach us yet? Not yet. We didn't reach 39. So we have 6 5s are 30. We're almost there. And then we could have a 7th whole that will give us another 5. 30 and 5 is 35/5. So we're almost to 40. So if we bring up another whole, how do we reach from 35 to 39? If we count it or we shade it, we recognize that there are only 4 of the parts that we need. We don't need all 5 parts. So that will carry us to the point of 35 and 4, which is 39. So this represents 39/5. And we can easily see from here we have 1, 2, 3, 4, 5, 6, 7 wholes and 4 parts out of 5, 7 and 4/5. And of course, the standard way that many teachers teach it would be like it's doing a division, where the numerator is the dividend and the denominator is considered to be the divisor. And how many 5s can we get into 39? Well, we know 5 8s are 40, so it's a little too much. So we can say, what's less than 8? 5 7s. So 5 7s are 35, and we will have a remainder. From 35, we're going 1, 36, 37, 38, 39. So the remainder is 4. So that tells us that the answer is 7 and 4/5. 36.48 divided by 6. And there are a couple different ways to do this. And some students can watch it and get the answer immediately, 6.08, while others may have some trouble analyzing it. So there are a couple different ways to do it. One way, I'm sure your teachers showed you this, would be taking the 36.48 and breaking it up into two parts, into the whole number, 36, and 0.48. So we can divide both of them separately. So we can say if we have 36, then 6 into 36, and that will give us 6. So we've handled the whole number. And that's how the answer had 6 wholes or 6 ones. And if we're looking at the decimal now, we can say 0.48, and we're going to divide it by 6. So 6 into 0 cannot. Bring down the point, and 6 into 48, we're going to get 0.08. And as such, 6 plus 0.08 will give us our answer. However, there are some students who are not too clear on what's happening with the decimals. So let's see if we could break it up a little easier for them. So let's look at the idea of the 0.4. So if we think about it, remember your teachers would be bringing up something like this, and they would show you when you were doing decimals that we can take a whole and split it into 10 parts. And if we split it into 10 parts, then how do we represent 0.4 or 4/10? Well, we can shade one of them, so that will give us 1/10 or 0.1. We can shade another one, which will give us 2/10 or 0.2. Another one, 3/10 or 0.3. Shade another one. So we've shaded 4 of the 10 parts. So that's 4/10 or 0.4. And if we're trying to figure out what's happening with the 8 is in hundreds. So if we overlay another group of 10 running horizontally this way, now what do we have? We have 10 tens. So we've broken up the whole. Just now we broke it up into tenths, and now we broke it up into 100 parts. So our 4/10 just now is the same as 10 and 10/20 and 10/30 and 10/40 parts, 40 hundredths. So 4/10 is the same as 40 hundredths. And of course, we have to add that 8 hundredths there. So this is what represents 48 hundredths. So 0.48 is the same as 48 hundredths, and we can simply do a division, 6 into 48 hundredths, and that will give us 6 into 48 is 8 hundredths. And what is 8 hundredths? 8 hundredths can be represented as 0.08 decimally. As such, if we had the whole number, 6 into 36 was 6, and we divide the decimal, which was 6 into 48 hundredths is 8 hundredths, which is 0.08, and we add, we will get 6.08. Number 5, write the missing numeral to make the number statement correct. 14 multiplied by 10 plus 14 multiplied by 7 is equal to 14 multiplied by what number? So, some students can easily identify it as 17, and some others need a little support. So let's take a look at it. This may be one of the ways that your teacher explained it in class. 14 multiplied by 10, we can look at it as a rectangle, where one side is 14 and the other side is 10. So it's like saying the length and the breadth, and we're finding the area. And let's look at the other rectangle. It is 14 multiplied by 7. So both rectangles share a side of 14. So one side will be 14 for the second rectangle, and the other side will be 7. As such, if we're trying to combine them, Then we have the rectangle on the left side plus the rectangle on the right hand side, and that will give us one big rectangle whose side is 14 and the other side is 17. So we can see that our answer would be 14 multiplied by 17. And this is similar. If students are still getting problems, let's use smaller numbers so we can see the idea. If we consider we have 2 multiplied by 5 and 2 multiplied by 3, well, we know 2 5s are 10 and we know 2 3s are 6. So that is something you students should be looking at. If you're looking at a question and it looks a little difficult, take the same question but use smaller numbers and see if you can work it out from there. And then apply it to the larger one. And what is 10 plus 6? 10 plus 6 is 16. So since we're looking at 2 multiplied by something, how do we get 16? 16 will be 2 multiplied by 8. So where did this 8 come from? If we had 2 groups of 5 and 2 groups of 3, then we could say 2 groups of 5 plus 3. So that 5 plus 3 gives us 8. And it's the same thing that was done above. One length was 10 and the other was 7. So we added them up together and got 17. Or some students prefer this method where we see we have a group of 10 and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tens, 11 tens, 12, 13, 14. So we have 14 groups of 10, which is our first brackets, and we have a group of 7. And how many groups of 7 do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14 groups of 10 with the green balls, and we had 14 groups of 7 with the red balls. So let's now look at this rectangle that we're putting around it. And what do we have? We have one group of 17 balls. And how many groups of 17 do we have? We have 14 groups of 17. Number 6. What is the square root of 121 plus 9 squared? So when we think about square root, it deals with having a square. So let's bring up a square first of all and recognize that if we're thinking about the area of a square, let's say that is 121, and the square root is actually asking us to figure out how long is each side. Remember, the length and the breadth is the same because it is a square. So do we remember our square numbers? If not, we can make a little list. 1, 2, 3, going up the road, let's say maybe 15 or so, we can stop. And if we're squaring a number and it ends with 1, which one of those numbers end with 1 when we square it? If we say 1 times 1, that will end with 1. And remember, we have number bonds we learned from infant 1. What number, when we add to 1, will give us 10? Well, 1 and 9 gives us 10. That's a number bond. So if we think of 1 squared, it will end with 1. If we think of 9 squared, it will end with 1. What else ends with 1? Well, something that ends with 1 again, which is 11. 11 squared will end with 1. And if we had a number bond, then 19 squared would be the next one that ends with 1. Now, there's a little trick to help us figure this out quickly. We know 10 squared is 100. So we want 121. So how do we get that? It has to be a number bigger than 10. So let's see, the next number we have bigger than 10 is 11. We know 11, when we square it, ends with 1. And let's see if we remember our 11 times tables. If we don't, that's okay. You know what 9 11s are. If we have 9 sets of 11, 9 11s are 99. And if we add one more 11 to that, it will mean that we have 10 sets of 11s. Or 99 and 1 is 100. 110 is 110. So 9 groups of 11 is 99. 10 groups of 11 will give us 110. And we want to find out 11 groups of 11 because we want to find out what is 11 squared. And if we add that, we're going to get 121. So what that tells us is we have 11 11s will be equal to 121. Or let's say it a little differently. We have a row with 11 in it, and we have 11 rows of 11. So if we have 11 squares making up a row, then 11 rows of 11 will give us 121 squares. So what is the square root of 121? If we work backwards, that will be 11. And then we can do something similar for 9 squared. 9 squared, we're using the word square. So let's bring up another square. And we want to find out what is 9 squared. So that means we can imagine we have 9 rows of 9. So 9 squares make up a row, 9 little squares, and we have 9 rows of 9. So how many squares is that in all? So we can add 9 plus 9 plus 9, and we keep repeating that 9 times. Or a little faster way, remember multiplication is just like we're adding over and over, repeated addition. So we can do it that way, or we can save some time and recall what 9 nines are in our tables. And some people know it immediately, and some people get a little problems with it. Remember, after the 2 times table and the 5 times, 9 times table is the easiest table to learn. There are so many different ways to know the 9 times table. I'm sure your teacher has showed you them. One of the ways will be we can easily write the numbers from 0 to 9. So let's do that. So let's write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Everybody can write those numbers. And let's write it again a second time. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's it. We've gotten our 9 times table. Because 1 9 is 9, 2 nines are 18, 3 nines are 27, 4 nines are 36, 5 nines are 45, 6 nines are 54, 7 nines are 63, 8 nines are 72, 9 nines are 81. So if we have those small squares, we have 9 rows of 9 small squares will give us 81 squares. So 9 square is 81. And now we can just go and add it on the side, 11 plus 81. And usually our teachers show us to add the ones first. Well, 1 and 1 will give us 2, and 8 and 1 will give us 9. So our answer is 92. Number 7, 5 minus 3/4 is equal to, and there are many different ways to do it. So let's look at bringing up a model where I'm sure your teachers had done this using a number line, and we're accustomed with using whole numbers on the number line, and we're dealing with what fractions? Quarters. So if we have 5, let's indicate that there, and we're subtracting, means we're moving to the left on the number line. So we'll be moving back 3/4. So we move back 1/4. From 5, it will give us 4 3/4. We'll move a second quarter, it will be 4 2/4. And by the time we move back 3/4, it'll be 4 1/4. So we can easily see what the answer is. And just for another representation, remember that if you wanted to try to draw a number line, there's no reason that you needed to start at 0. So we could have started at maybe 3 and just go up to 5 or 6 and then work the question from there. So it would save us some time. Another way to represent this is by using circles. And of course, since we're using fractions of a quarter, it means we're splitting the circle into 4 parts. And how many circles do we have? We have 1, 2, 3, 4, 5. We have 5 circles. And if we consider 5 circles, and from there we are going to subtract or take away 3/4, it means that what are we left with? We are left with how many holes? 1, 2, 3, 4 holes and 1/4. So 4 1/4. And some teachers may be guiding their students to do it in a more procedural approach, where we could think about 5 holes is 5/1, and we can change that to something out of what denominator? Out of 4. Because 3/4 means that we're cutting a hole into 4 parts. So how do we move from 5/1 being an equivalent fraction to something over 4? Well, how do we go from 1 to 4? We're getting bigger. So we multiply. And what do we multiply by? We multiply by 4. So 1 times 4 is 4. And if we multiply by 4 below in the denominator, we shall do the same on top, because we want to maintain that it's equal. So 5 times 4 is 20, which gives us that 5 is 20 over 4, or 20/4, minus 3/4. And if we have 20 of an item minus 3 of the same item, 20 minus 3 is 17. So we get 17/4. And even in our diagram with the circles, we can easily see we had 4 holes, which gave us 4 sets of 4, which is 16/4. And we have 1 more quarter in the last hole. So that's 17/4. And we can also represent it using 1, 2, 3, 4, and say 4 triangles makes a hole. And how many holes do we have? 1, 2, 3, 4, 5. And if we did the question like this, there are so many different ways we can do fractions. And if we have 5 holes and we subtract 1/4, 2/4, 3/4, what are we left with? We are left with 1, 2, 3, 4 holes and 1/4. Number 8. Write the total value of the bills and coins. And we can see from there, we have 1, 2, 3 dollar bills, and we have 1, 2, 3, 4, 5 coins. So we can add them up. Let's take the dollar bills and find the total first. So we have $5, and one more is 6, and one more is a total of $7. And remember, we can write the $7 by putting a 7, putting a decimal point, and 2 zeros. The 2 zeros to indicate that there are no cents. And just as we added up the dollars, we can now go and add the cents together. So we have 25 cents, and another 25 cents is 50 cents, and 25 cents is 75 cents, and 5 is 80, and 10 is 90 cents. And we want to write it in a similar format as the $7. So we can write it as $0 and 90 cents. So we're adding them up in parts. If we put them together, we have $7.90. Some teachers also show the students to write them down individually. So $5 is 5, putting your point to show that you're moving from $1 bills to cents, and then 2 zeros. And we're adding that $5. We're going to keep adding $1 and another $1 and 0.25 to represent 25 cents. Be careful with the 5 cents. Remember, it is 5/100ths. So it goes into that second column after the decimal point. So 0.05. And 10 cents will be 0.10, because 10 cents is really 1/10 of a dollar. So it will be in the place value column right after the point. And now we can add it. We usually start from the teachers showing us it on the right hand side. So that will give us 5 cents, and 5 cents is 10 cents, and 5 is 15, and 5 is 20 cents. So now that we've written that, we want to use the 1/100ths values, which is on the extreme right, and that is 0. So we can put that in that column. And now we're going to add the tenths or 10-cent values. So if we're coming down, we have 2 and 2 4 and 2 6 and 1 7. And we have 2 extra from before when we did the 20 cents. So we had 2 10-cent pieces here. So that gives us a total of 9. And that means that we have 90 cents. So let's put our point. And now we can add the ones, which is the value to the left of the point. So we have 5, 6, 7. So that gives us $7.90. 312 multiplied by 15. And there are quite a few different ways to do this. So let's recall that when we're thinking about multiplication, it is the same idea as what we have done in geometry in finding the area. So if we consider we have a rectangle where one side, the shorter side, we can say that's 15, and the longer side will be 312. Then when we're considering finding the area of an object, we can consider that there are 15 rows across with 312 small squares in there. And we need to find how many squares are there in all. That's the same as saying finding the area. So if we're doing that, then we can break it up a little bit. So we consider the whole length being a smaller rectangle of 300 and another rectangle of 10, that's 310. And what remains? 2. So it's a large rectangle, 312 across, multiplied by 15, but we can break it up into parts. 300 by 15, 10 by 15, and 2 by 15. And we know our 15 times table from the clock. 115 is a quarter turn, which is 15. 2 15s is a half turn or half an hour, which is 30. And 3 15s will be 3/4 turn or 45 minutes. So 3 15s are 45, and we have 2 zeros because it's 300s. So 300s times 15 is 45 hundredths or 4,500. And now if we're multiplying 10 times 15, remember the shortcut rule. If we're multiplying by 10, we just need to add a 0 to the 15. So it will be 150 or 150. And then 2 times 15, as we said, that is 115 is a quarter turn, 15 minutes on the clock. And 2 15s will be 2/4 turns or a half turn, which is 30 minutes. So now how do we get our answer? Our total will be 4,500 plus 150 plus 30. And we just need to add it up. So if we're adding, let's add up all the ones values first. So that will give us 0. And if we look at the 10 values, we have 5 tens and 3 tens. That's 8 tens. And then the hundreds, we have 500 and 100 is 600. And we have thousands, only 4,000. So we've gotten our answer. So the answer for 312 multiplied by 15 is 4,680. And the question is done. And if we take a look at this, what did we really do? We really multiplied 312 times 15. And that is the normal algorithm that we use in school. Or we can do it another way, where we bring up the same idea of area, and we have a large rectangle where one side is 312 and the other side we can break up into parts. We can break it into two rectangles, one being a width of 10 and the other with a width of 5. So 10 plus 5 is 15. So it's like asking us to find the area of the large rectangle, 312 multiplied by 15. And we can do it by finding the area of 312 times 10. And if we're multiplying by 10, we just need to add a 0. So it'll be 3120, 3,120. And for the other rectangle, the smaller one, it will be multiplying 312 times 5. And we can do multiplication, or we could think about it differently. Since 312 times 10 is 3,120, and we want to multiply it by 5, then we really want to find half of 3,120, because it's not 10 sets of 312, but 5 sets of 312. So we can actually, instead of multiplying, do it differently and divide 2 into 3,120. We're finding half of that. And let's do a little division. 2 is going to be into 3,000. And if we have 3,000s, 2 into 3,000s, how many groups of 2 can we get? We can get 1,000. And we will have a remainder of 1. That remainder of 1 is 1,000. And now we can put it with the next one, which is hundreds. So if we're moving 1,000 and we're carrying it across the hundreds, 1,000 is the same as 10 hundreds plus 100 we have there will give us 11 hundreds. And your teacher would have explained this many times using base 10 blocks and showing regrouping. So we now have 11 hundreds and we're forming groups of 2. So how many 2s can we get in 11? And that will be 5. So we have 5 hundreds and we will have a remainder of 100. What do we do with that remainder? That 100 will now join with the 2 tens. So 100 is 10 tens and we have 2 tens. So that gives us a total of 10 and 2 is 12 tens. So 2 into 12 tens is 6 tens. And 2 into 0 is 0. So we actually have the area of the smaller rectangle, which will be half the area of the larger rectangle. And now to find our total, we can just add it. 3,120 plus 1,560. And of course, if we're adding, we start with the ones value, 0 and 0 will give us 0. 2 and 6, 6, 7, 8. 5 and 1 more is 6. 3 and 1 more is 4. So it supports our answer of 4,680. And of course, what did we do? We actually multiplied 312 multiplied by 15. Number 10, write the missing numbers in the boxes below. And if we look at the numbers, we can see we have 430 something because we don't know what that is. So I indicated it with a green box. Added to 900, we don't know how many tens, so we have that in a blue box, and 7. And when we add these two, it will give us a total of 1,345. So there are a few ways to do this. So let's recall that you may have been accustomed because your teachers were using base 10 blocks in classes. So we can represent it just as that. So for the first number, remember we want to put in the place value just to give us a little support to remind us where the ones, the tens, and the hundreds are. And if we're going to explain that first number, it is 400s. So that each one of these represents a square 10 by 10. So your base 10 blocks shows you that's 100. And we have 4 of those, 1, 2, 3, 4. And what else do we have? How many tens? 1, 2, 3. And of course, how many ones? We are not sure, so let's put a green box. And let's now look at the second addend. When we're showing what is that, how many hundreds do we have? We have 1, 2, 3 hundreds, and this number is supposed to represent 9 hundreds. So 3 more, 3 and 3, 6, and 3, 9. So we have 9 hundreds. How many tens? We don't know. And how many ones? Well, we have 5, and 1 more, 6, and 1, 7. So this here indicates the two numbers that we need to add. The first row up on top tells us it's 430 something, and the second set tells us 900. We don't know how many tens and 7 ones. And if we add it up, it's going to give us 1,345. And we can either use the 1,000 as a big cube, as we see it in the base 10 blocks, or consider it 1,300 is really 1,300s. So we can bring that up 3, 6, 9, 12, and one more 1,300s. So that tells us something. If we look at what is above, we had 4 hundreds, 4 squares 10 by 10, and 9 more. So it's a total of 1,300 above. And when we add those two, 400 plus 900, it gives us the 1,300. So therefore, the hundreds column with the thousands is already taken care of. So what are we left with? We are left with 3 tens or 30 and some ones, which we don't know, we have in green, and some tens in blue, and 7 ones. So if we think about that, then that gives us 45. So we could see it in the bottom half. We have 4 tens and 5 ones to represent that. So the question has now come down to a question dealing with ones and tens. We have 3 tens and some amount of ones in the green box. We don't know how many tens in the blue box, and 5 ones will give us 45. 4 tens and 5 ones. So let's think about what's happening in the ones column. If we think about what number can we put in there? Can we put 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? One of those digits are going to fit in there. So which digit can we use so that when we add 7 to it, it will give us a number ending with 5? 0 and 7 does not end with 5. And you can check 1 and 2, and you will see that the answer will be 8. So 8 and 7, let's count it, 8, 9, 10, 10 and 5, 15. So that tells us 8 and 7 gives us 15. And we could represent the 8 with 5 and 3. So that's 8 units and 7 units. And if we add it up, 8 and 7, we can say 5 and 5 is 10, 10 and 3, 13, and 2 more, 15. So that means those 8 units, or 8 ones and 7 ones, will give us 15. And 15 is represented as 1 10 and 5 ones. So now what do we have in the tens column? We know we have 3 tens on top, and we need to add a certain amount of tens in the blue box to give us 3. So we already have the 3. As such, our answer is 0. So that means it's 907. So we've solved our question. 438 plus 907 is 1345. And after the first part of the question, we recognize that the 400 plus the 900 gave us the 1300. So it really came down to 38 plus 7 is equal to 45. Number 11. What is the distance in centimeters between point P and point Q? And if we think about where it's starting with the green arrow indicating at 18, and we want to know how far it is from P to Q. And there are a couple different ways to do this. Let's recall that this is actually part of a ruler. So the ruler actually runs straight across and it doesn't fit anymore onto the page. So we can slide the ruler because we know the length P to Q, and we can slide the ruler across until when we're measuring, we always start at 0, and the 0 will indicate the starting point at P. And now we can show where it ends with the purple arrow at Q. So that tells us our length is simply by reading off from the ruler 6.5 centimeters or 6.5 centimeters. Either one is correct. And some teachers prefer if we actually do some working in terms of saying 24.5, which is our final point at Q, minus 18, our starting point. And 24 minus 18 is 6. And we have a half, 6.5 or 6.5 centimeters. Others would like another method would be to go from 18 to 24.5 by counting with the number line. From 18 to 19 is 1, 19 to 20 is 2, 21 is 3, 22 is 4, 23 is 5, 24 is 6, 6.5. By jumping, like using it as a number line. Number 12. Read the time shown on the analog clock. Write this time on the digital clock. So let's recall that when you're looking at the analog clock, the one on top, then we can first look at the hour hand, which is the shorthand. And if we take from the center and we extend the line, we can see that it has passed the 4-hour mark. And if we extend again, we can tell that it has not reached the 5-hour mark. Because if it reached the 5-hour mark, then let's look at the minute hand. It would have moved from 8 and go up 9, 10, 11, 12, until then it would be 5 o'clock. So it's not 5 o'clock as yet. As such, the hour hand on the digital, we can say for sure it's at 4. Now let's recall that we already had the hour hand. We want to look at the minute hand now. And we can split the clock in half. And we know at 6, it is half past or 30 minutes. So at 7, it'll be 35. And as such, at 8, which is the present time, it will be 40. So it's 4:40. But there are other ways you can do it, where we can split the clock across as well. So we get it into 4 parts. So at the first quarter turn, which is at 3, that's 15 minutes. And then at half turn is 30 minutes. And at 3/4 turn, which is at 9, 9 fives are 45. So we haven't reached 45 as yet. We're actually one movement less than 45. So at 8, So it will be 40. That's another way to do it. Or for students who want to be very sure, they can say 1 5 is 5. That means 5 minutes. 2 5s are 10. 3 5s are 15. 4 5s are 20. 5 5s are 25. And continue until they reach the point of 8, where 8 5s are 40. So this analog clock can be represented at the time of 4:40 on the digital clock. Number 13, the calendar below is torn. What would be the date of the fifth Friday? So we're seeing it's November 2019 because this is the SEA paper 2019, and we have it written in a standard format from Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. And we're interested in what's happening on the fifth Friday. We know the first Friday is on the first of the month, the second Friday is on the 8th, and the third Friday is on the 15th. So there are a couple different ways we can solve every single question. So in this format, one way we can do it is we can actually put back on the rest of the calendar. Let's draw it out ourselves. And let's recall that each one of these rows is actually a number line, and it just shows a portion of the number line. So the last row is from 10 to 16. So that continues 17, 18, 19, and so forth. So we can actually slide the number line across, carrying it so that it starts the next row at 17. And that's what's happening at each row of a calendar. It moves across 7 spaces because there are 7 days in the week. And if we recognize that, then we have 1, 2, 3, 4 Fridays accounted for. We actually want the fifth Friday, which will be in the following week. So let's take our number line again and move it. And as we slide it across 7 places, it will start the next week on the 24th, because the week before ended on the 23rd. Saturday the 23rd, as such Sunday the 24th. We are well accustomed to this. So we can tell now the fifth Friday would be the 29th. Another way we could have done this is recognize that if the first Friday is on the 1st, and then to move to the second Friday, it's the 8th, meaning we're adding 7 to it. And moving from the second Friday to the third Friday, we're moving from the 8th to the 15th, we're adding another 7. And we have to move 2 more from 15 to 22nd to get the fourth Friday, and another movement to get the fifth Friday. So some teachers would encourage us to write 15 as being the third Friday, and we're adding 7 and 7, 14 more days to get the fifth Friday. So 15 plus 14, and simply we can do simple addition where when adding 5 and 4 will give us 9, and 1 and 1 will give us 2. So the fifth Friday is the 29th day of November. Number 14, the solid below is made up of cubes of the same size. And from the dimensions given, we can see that the length, the breadth, and of course the height, all three will be the same for a cube, which in this case is 2 centimeters. So the question asks, what is the total volume of the entire solid? So let's take one of those cubes and extract it and make it larger so we can see it easily. And let's take off the color now. So we can see that it's 2 centimeters by 2 centimeters by 2 centimeters in all 3 directions, length, breadth, and height. And what we want to do is fill it up with 1 centimeter cubes, meaning a cube which is 1 centimeter by 1 centimeter by 1. So we can see that one of those, we have it in green, fits at the back right side corner. and there's space for one to fit in front of it. So we get two cubes coming towards us, and one in the back again, and one in the front left side. So that means the base of this, we are able to fit 4 cubic centimeters. And if we have 4 at the bottom, that has not filled the entire thing as yet. So we could put one on top, one in front. So that gives 4, 5, 6, 7, 8. So what does that tell us? It says that the volume of one cube will be 4 and 4, 8, which means 2 times 2 at the base times 2 as the height. Some of our teachers will tell us we must learn length times breadth times height, which is 2 times 2 times 2, which is give us a volume of 8 cubic centimeters. So we have, for each one of those purple cubes, it takes up a volume of 8 cubic centimeters or centimeter cubes. And how many do we have in all? Because we want to find the total volume. So what we can do, we can slide off the top layer and let's count it. In the base layer, we have 1, 2, 3, 4 cubes going across and 3 rows of that. So that tells us 3 fours are 12 in the bottom layer and 12 in the top layer, which means we want to find the total volume, which is made up of 24 cubes. Since one cube takes up a space of 8 cubic centimeters, 24 cubes will take up a space of 24 times 8. And we can go on the side and work out that short multiplication, 24 times 8. And we can say 8 fours are 32. And for students who are getting problems with regrouping, then we can write it like this. 8 fours are 32. And then we want to multiply 8 times, not 2, 8 times 20. So 8 times 20 would be 160. And of course, we're going to add it up. And that will give us 2 and 0 is 2, 3 and 6 is 9, and 1. So 192. Therefore, the total volume of the solid is equal to 192 cubic centimeters or 192 centimeter cubes. They both mean the same thing. Number 15, on the diagram below, which two angles are greater than 90 degrees? So if we look at this, remember when your teacher was doing measurement with you and looking at the idea of angles, one of the things that they did with you was to use paper and make angle testers. So you were able to fold the paper to make a 90 degrees, a 45 degrees, maybe a 60 degrees as well, right? So that way you can take your own tester and check to see what size the angle is. Later on at secondary school, you'll be using a protractor which does the same thing. So let's show a little one on the side. Imagine we have a circle, and of course we can split that circle in half, and we can split it again into quarters. So we can see 4 quarter turns, and one of those quarter turns is 90 degrees. So we can use our 90 degrees tester, which you would have made with paper. You can do that in the exam and check each angle. So let's do that. Let's take the angle tester and move it across to A. And remember, what is an angle? It's the measure of the turn. So we have the arm and it turns. The arm was facing from A to D and it turned upwards to face B. So how much did that turn? Did it turn as much as 90 degrees? No, it turned less than 90. And the question is asking for which angles are greater than 90. So A is not 1. Let's try it again. Let's go to B and we turn it. And we can see now our 90 degrees and B has turned an angle greater than 90 degrees. Let's do the same for C as we slide it up. We have to turn it into position and look at how much C has turned. That angle has turned less than a quarter turn. So C is not an angle greater than 90. And finally, let's check D. We'll have to turn it the other way, an anti-clockwise direction. And we can see what a quarter turn is, and D has turned more than that. So D is also an answer. So the angles B and D in this parallelogram are greater than 90 degrees. Number 16, name one solid with a uniform cross-section. So if we recall what that means when Sir or Miss did it in class, it means that if we have a solid, a three-dimensional shape, and it is such that when we cut it, we see the same shape in the middle as we see on the ends, then it has the same or uniform cross-section. And there are many different answers that will work here. Let's show one. Imagine that at the bottom of our object, we have a circle. And if we put another circle on top of it, let's say it's a little thick so we can see it, and we build it up again with another layer. Each layer, so imagine if we cut it, every time we see it, we have another layer and we're seeing the same size circle. That means it's uniform cross-section. And we say it again. So that cross-section, that piece, if we cut it across, we're going to see the uniform or the same circle. We put it again. So that means that what shape is this that has a uniform cross-section? That is a cylinder. We'll do one more solution as there are so many different ones. Imagine we have a rectangle at the base and we have one on the top. Then this here means that if we cut it somewhere here, we can see a rectangle the same size as the base or the top. So the cross section is the same, it is uniform. If we do it again, we see the same cross section, and the third one will reach the top. And what shape is this? This is a cuboid. It will also work for a cube, for a triangular prism, or any of the other prisms. Number 17, which plane shape A, B, C, or D below has all the properties described in the table, which are one pair of parallel sides, one pair of equal sides, and one line of symmetry. So let's look at the idea of parallel sides first of all. And let's look at the first shape, shape A. And we can see that the two horizontal sides or flat sides go in the same direction, and they will, even if we made it longer and longer, they will never touch each other. They will have the same distance apart. Then those two red lines, we have arrows on them to show that they are parallel. So we have one pair of parallel sides in shape A. So it works with the properties. Let's remove it and let's look at the other two sides in shape A. Both of them are facing vertically. So those two are also parallel, which means that shape A has two pairs of parallel sides. As such, it does not hold for the property of parallel sides. Let's look at shape B. In shape B, let's look at the sloping sides coming down to the right, and we can see both of them are with the same slope, pointing in the same direction. So that means it has one pair of parallel sides. Let's remove it, and let's look at the next set of sides, and we can see that both of them are also parallel. So we also have two pairs of parallel sides here as well. That means B does not have one pair of parallel sides only. So A, which was a rectangle, did not work. B, which is a square, just tilted sideways, does not work as well. So let's look at C. And we have a right angle triangle. Do we have any pairs of parallel sides? One side is pointing up, one side is flat, and the other one is at a slope. So there are no pairs of parallel sides there. Since A, B, and C are not the answer, then clearly it must be D. So let's check D. Let's look at the two sides on the left and right. So let's look at the one on the left first. We have it in blue. And how long is it? From the time it started to where it ended, it moved 1 unit across and 2 units up. And let's look at the other slope, 1 unit across and 2 units up. So the two blue lines in D are having the same length. Now let's look at the other sides. The top and the base are both parallel. So we have one pair of parallel sides, we have one pair of equal sides, which are in blue. And is there any line of symmetry in this? Can we fold it on an imaginary line so that one side fits exactly over the other? That will be a line of symmetry. And we can see this brown line here shows us the line. So this is considered to be an isosceles trapezium. It's an isosceles because it's the same on both sides, right? The same lengths. And it's a trapezium because we have one pair of parallel sides, and it follows those properties. Number 18, the pictograph below shows the pets owned by 90 children. And if we look at it, we can see what are the types of pets that the children own. They own dogs, cats, birds, and fishes. How many children does that symbol represent? So if we look at this little guy and we take a look at the dogs, we can see that there are 1, 2, 3, 4, 5. So there are 5 symbols or 5 little guys that represents how many children own dogs. And let's add up how many cats there are. 1, 2, 3, 4. So there are 4 symbols to represent how many children own cats. And similarly, let's look at the birds. 1, 2, 2.5 birds. And of course, how many fishes? 1, 2, 3, 3.5. As such, if we want to find out how many in all, we can add up the whole numbers. 5 and 4, that's 9. 9 and 2, that gives us 10, 11. 11 and 3, 12, 13, 14. So we know that there are 14 wholes. But we also have fractions. We have half plus a half, and that gives us 1 whole. So in all, we have 14 plus 1, which is 15 little guys to represent the pets owned. So let's go back to the question up on top. The pictograph below shows the pets owned by how many? By 90 children. So what we can say is that 15 of these little guys represents 90 children. So how much does one of them represent? 90 divided by 15. And we all know our 15 times table because our teachers have done this with us many times. So let's revise it a little bit. Let's bring up a clock. And if we think about the hand starting there, our minute hand is at 0. And if we take 1/4 turn, that means we've moved 15 minutes. And if we take a second quarter turn, that means we've moved 30 minutes. So each quarter gives us 15. So 1 15 is 15, 2 15s are 30. Let's move again. So 3 15s will give us 45. And by the time we make 4 15s or 4 quarters, we get a whole 1 hour or 60 minutes. And we're doing our 15 times table. If we go again, it will give us 75. That's 5 of them. And if we go one more time, that will give us 90, which is 6 of them. So how many 15s are there in 90? Well, it tells us that the little guy represents 6 children. Number 19, the tally chart below shows the favorite colors of some students. And if we look at the chart, we can see in the first column, the different colors are identified. Some students' favorite color is red, some are blue, some students' favorite color is yellow, and some favorite color is green. And the second column tells us the number of students. What color represents the mood? So let's recall, what does mood mean? M-O-D-E, mood. It means the M-O-S-T, the most. So which one of those favorite colors do the students love the most? So that's easy for us. We can take a look at red, and if we count it up, 1, 2, 3, 4, with the cross stroke, let's recall that in a tally chart, that indicates 5, and then we have 6, 7, 8. And with blue, 5, 6, 7, 8. In yellow, we have a group of 5, another group of 5, that's 10 students, and 2 more, 11, 12. And those students whose favorite colors are green, it's 1, 2, 3. So easily we can see that there are 8 students who love red, 8 with blue, 12 with yellow, and 3 with green. And they're asking us for which color do the students love the most? And that is yellow. Number 20. The table below shows the number of ice cream cones sold for 3 days. So it indicates that on Monday, we sold 25, Tuesday, 18, and Wednesday, 35. Calculate the mean number of ice cream sold. So this is a statistics question, and we need to know what the word mean indicates. Mean, as explained by your teachers so many different ways, really tells us that we would like to take those 3 days and redistribute it so that it is as if we have the same amount of cones sold each day. So let's bring up a little diagram as your teachers would have done in class, indicating for Monday we had 25. On Tuesday there were 18 of them sold, and on Wednesday, of course, 35. Since we know that we're trying to redistribute it or share it up equally for each day, could the average or the mean be 18? If we think about that, then Tuesday would be the correct amount, but we would have extra on Monday and we would have extra on Wednesday. So what would we do with this? So 18 could not be the mean. So let's try 35. If 35 was the mean, then Wednesday would have the correct amount but we would be short of cones on Monday, 10 less, and we would be short of cones on Tuesday, 17 less. So 18 cannot be the mean, 35 cannot be the mean. So our mean or average should be somewhere in the middle. So let's take the idea that it is 25. If it is 25, then the first day has the correct amount already. The second day is short. How much is missing? How do we go from 18 to 25? If we count it up, 19, 20, 21, 22, 23, 24, 25. So we need 7 more. And where could we get that 7 from? Well, we have extra on Wednesday. So maybe we can take out 7 and bring it across to share it up evenly. But look what happens. Monday has the correct amount, 25. Tuesday, by redistributing, gave us 18 and 7, 25. So the first 2 days has ample amount. And on the third day, it was 35 and we carried 7 across to Tuesday. So 35 minus 7 now tells us we have 28. So we still have extra, but just a little bit. And that extra is on Wednesday. How much extra? If we remember, the red line says that we're 25 on first day, 25 on the second day, 25 on the third day. We have 3 more to make 28. So what do we do with that? We can share it up again. So we can take one of them from Wednesday and carry it across. So Monday we'll have 25 plus 1, 26. And then we have 2 more remaining on Wednesday. That's above the 25 marker. So we could carry 1 across again. So we have 25 plus 1 on each of the days. We have the even amount. That means that our mean or average is 26. So even though 25 cones were sold on Monday, 18 on Tuesday, and 35 on Wednesday, it was the same as if we sold 26 on each of the days. And that tells us our mean or average. The way that teachers will do it for the SEA preparation is they will say, well, we have 25 on Monday, and we have 18 on Tuesday, and we have 35 on Wednesday. So let's see if we could add up all together. And even in adding, there are so many different ways that different teachers show their students. One way is by adding all the ones. So we have 5 and 5, 10. That's an easier way to add. And 8, 18. And we can actually write the 18 right underneath it. No need to write it on the outside. As I say, every question in maths has hundreds of different ways to solve it. And now that we've added the ones, now let's add tens. We have a 2 in the first number, so that indicates 20, and 10 in the second number on Tuesday. 20 and 10 is 30, and Wednesday has 30 again. 30 and 30 is 60. So we got 18 and 60, and if we add it up, we can add the ones if you wish. 8 and 0 is 8, and 1 10 and 6 tens are 7 tens, which are 70. So our total cones that we sold for the 3 days was 78. And now what do we want to do? We want to find the mean, which means we want to be able to share it up equally across 3 days. So how do we share equally? Well, we think of 78, and sharing is division. So we can divide it, short division, long division, anyway. And now we do the simple division. Of course, just as a reminder, because your teachers do this all the time with you, we are trying to find how many groups of 3 there are in 78. So remember, we're not saying 3 into 7. That is not 7. That is 7/10. And your teachers would have brought in front of the class base 10 blocks to show you that, and photocopied some for you, cut it out and print it and gave you all. So you all are custom working with this manipulative. So how do we represent 70 or 7/10? By bringing up these rods. Each rod has 10 squares in it. So you may have been accustomed in your class with the paper cut out in tens already, or checkered line books cut out in tens and using them. So we have 1, 2, 3, 4, 5, 6, 7 tens. So that indicates we have 70 and we have 8. 5 units and 3 units. So that's 8. And if you don't have it and you want to practice, go cut out your checkered line book. If you want, you can photocopy it, make it a little bigger, right? And use it easier for you to practice with. Now, what do? We're finding groups of 3. So let's look at the tens, or what we call the rods. How many rods do we have? We have 7 rods. So we are not saying 3 into 7, we're saying 3 into 70, which is 3 into 7 rods. How many of those rods can we group into threes? Well, we can make a first group with 3 in it. We can make a second group of 3. Could we make a third group? No, we don't have enough. We have 1 remaining. So how do we indicate that? We say 3 into 7 rods, or 7/10, will give us 2 groups. And we will have 1 group of 10 remaining. So we normally put that here. That's how the teachers normally do it. So what is that telling us? We don't have 9. We have 10, 1 group of 10, and 8 units remain. So 10 and 8 is 18. So can we find groups of 3 now? Not as it is. So we need to remove that 10 and put in 5 and 5, 10 units. That is considered to be regrouping or trading. And now we have 5, 10, 15, 16, 17, 18 units. Can we find groups of 3? Well, 1 group of 3, 2 groups of 3, 3 groups of 3, 4 groups of 3, 5 groups of 3, and 6 groups of 3. So we can get 6 groups of 3 from 18. And of course, you could have done that quicker because you know your 3 times table. So 3 sixes are 18. So this is another way where you can show what the mean is, which is 26. We have now come to the end of SCA 2019 past paper questions in section 1, where we have done all 20 questions. Our next video will be looking at SCA 2020, the following year, and specifically at section 1 questions only, before we go on to others. Don't forget to look at the description down below, where we give links to all the section 1 videos and then the other sections. Goodbye.